All right. I'd like to encourage everyone to be on mute if you're not speaking. I'm Dr. Noel Schultz from Washington State University, and today we have our last for the semester CySER webinars. And today we're honored to have Dr. Clemente Izurieta. Oh, I didn't get that close, but
it's really good.
Who is an associate professor in computer science in the Gianforte School of Computing at Montana State University in Bozeman, and also the CTO of Authors AI and Binge Books from Orlando, Florida. His interests are in quality assurance, technical debt, and cybersecurity. He received his PhD in computer science from Colorado State University, his MS in computer science from Montana State, and a bachelor's of science in mathematics from the University of Wollongong in North South Wales, Australia. He's director of the Software Engineering Laboratory at Montana State and has 1 postdoc, 8 PhD students, 3 master's students, and 3 undergrads. Funding for that laboratory comes from the National Science Foundation, DoD, DHS, the Army, Air Force, and private industry. Prior to his career in academics, he spent 16 years at Hewlett-Packard and at Intel Corporation. He's a member of ACM and a senior member of IEEE. So I'll turn it over to him to go through his presentation on a hierarchical software quality assurance approach to leveraging existing technologies and building quality gates.
Thank you, Noel. I appreciate it. Boy, that's a mouthful for a title. I was thinking of a paper rather than a presentation. Maybe I should have changed the title. First of all, thank you everybody for being here. Good afternoon, and of course, thank you for the privilege of your time. I know it's difficult, especially this time of the year, right after Thanksgiving, and as we're getting close to exams. And so, what I'm going to talk about today, and I'm going to follow in the footsteps on some of the prior speakers here, is I'm going to give you a little bit of an idea of all the work that my lab is really concentrating on right now. And I'm going to focus, of course, on hierarchical quality assurance and what this is all about. But I've also reserved a little bit of time towards the end to tell you about some of the other work that we're doing, and also upcoming work, some of it in collaboration with Washington State University. A lot of the research that I'm presenting here today leverages existing technologies and investments that have already been made by a lot of organizations. And in fact, this is some of one of the criteria that we've always had from the beginning. There's so much technology out there, and you want to leverage as much of what's out there rather than trying to reinvent the wheel every time. And so our goal is really to encourage organizations to continue to use what works, in their space. Just really quick, that's a picture of Bozeman. It's approximately 50,000. I like, whenever I visit Pullman, I really like it because it seems to compare in terms of size. It's kind of a little, kind of community. And I have a fun time whenever I visit you guys over there. We're smaller. We have 17,000 students. But my lab have grown significantly in approximately 4 years, and this is when we started taking a turn towards cybersecurity. So let me tell you a little bit about what we're going to talk about today. First, I'm going to focus a little bit on quality assurance, and that's because by trade, that's really my training. That's where most of the work that I've done in the past comes from. And I'll tell you how I got into cybersecurity and how I got involved in that. I'm also going to talk about a total quality index. These are some of the concepts that got us really engaged, very specifically with CISA and with the Department of Homeland Security. A little bit about quality gates. I'll give you some of the example models that we've been working with and some of the ones that are deployed, especially with Army. And then I'm going to tell you about the software engineering lab current work in some of the other areas that we're exploring. At the end, I reserved a little bit of time to tell you about ARL. This is our applied research laboratory that's here on campus as well, that allows us to do classified work. Okay, so let's talk a little bit first. I wanted to give you a quick background, and again, you don't have to become an expert on this, but this is you know, a lot of quality assurance models tend to be theoretical. That's what you see here. It's basically, you know, a list of characteristics and sub-characteristics, and this goes, this is not just 2 levels in this tree, but really, whenever you read some of this, these booklets that contain all these ISO standards, for example, they don't tell you anything about how you operationalize a lot of these things. So this ISO model that you're seeing here, we basically focused on this one as a result of our partners. They've asked us to focus on the ISO 25K. As a note, by the way, most of the work, and as I told you earlier, that the software engineering lab has done here is on quality assurance. It's not on cybersecurity. And so approximately 4 years ago, we were approached by DHS because we wrote a white paper to them with the quality assurance perspective on cyber, to see if we could develop some of these similar technologies, these hierarchical quality assurance techniques, but really to focus it on security, right? So where you see there that one little characteristics with confidentiality, integrity, et cetera, that you see in this slide, but just focus on that. And so we started the process first by trying to operationalize this ISO 25K and focusing on something called RMF. RMF is the risk management framework that a lot of government organizations need to adhere to. Okay, so let's look at this picture for a second. So let's describe this a little bit. So even though the ISO quality models offer, you know, some good, valuable, they paint a picture of the landscape for addressing software quality. It doesn't really provide the means to measure or assess quality in real-world applications. Okay, so in order for us to do that, you have to be able to operationalize this ISO model. And in here, what you see on the left-hand side, you know, you have the ISO. This is a generic picture of a theoretical model that has quality at the top and then all the sub-characteristics. Models like ISO 91, the 9K, the ISO 25K are very similar. You have NIST 53 and 82 and risk management framework. On the right-hand side, what you see is an operational quality model. And operationalizations of quality models require that you figure out a way to actually provide a quantitative score when you're capturing a quality attribute or a property of a particular product. We typically do that through tools in our environment. And the models that you see here precede a lot of the work that we did. Kuomoko in 2012 from Wagner, he developed this operational quality assurance model that was focused on the automotive industry in Germany. They were very successful with this. And then there was a follow-on called Catch. And then we basically took some of the drawbacks that some of these operational models have. And then we took some of these models that had already been in place. Okay, welcome unknown. And then we developed the peak model. And the peak model has been in place since only about last year when we started operationalizing a lot of these concepts. Okay, so what the key here is that at the very bottom, you're going to have tools. Okay, and tools provide actual measures that are quantitative and they feed up the tree to provide a quality score that allows you to aggregate a lot of the scores from a bottom-up approach. Of course, there's a lot of nuances associated with aggregation, right? It's not as simple as just finding averages. So we developed a technique or a platform called PEAK, and I'll tell you what it stands for in a little bit. But basically what you see here is a simplified version of really the abstraction of PEAK. At the very bottom, you have tool output, and this comes from tools that an organization may already have in place. We have some organizations that, buy tools that cost a lot of money, and they don't want to, do away with that. They want to leverage that investment. The findings that we find from a lot of tools, we map them to something called diagnostics, in what you see there in the measurable concepts slice of this picture. They go through what we call utility functions. This is a way to benchmark a diagnostic and to normalize a diagnostic so that we can compare apples to apples, right? And we have papers on this, and I don't want to get into this, but I think we all understand the concept of normalization. Well, once we have a measure, then you start getting into the business level goals at higher levels on a tree. And these are more typically what management cares about. And when I say management, this is me speaking from a software engineering perspective, right? Managers care about the reliability, the maintainability, the usability, all the ilities of your software. And they actually quantified this using dollars per hour spent. And so there are dashboard technologies out there that help show this tree. So the higher up you're in the tree, think management. The lower you're on the tree, the more specialized you become, think developers. Okay, so let's look a little bit about where these quality gates, or when you instantiate one of these trees that I just showed you before, when you instantiate one of these things, let's see where they fit a little bit. So what you can see here is just a slice. This is one of many of how software can really make its way from the vendor, which is on the left-hand side of your picture, all the way to production. The picture that you're seeing here is actually representative of what we see on one of our Army partners. And so the arrows just represent the flow of software, nothing special. And what you see in here, the peak icons represent our technology of basically an operational gateway. These gateways basically can assess the quality of the incoming software, all the ilities that I showed you from an ISO. Again, we want to focus on security weaknesses, and we can look at all sorts of. We can make this models, very compact and micro, using parsimony, right, as a rule of thumb, which makes them a little bit more, I would say, accurate. Or you can make it as wide and large as you want, but you tend to lose some of the fidelity that you're looking for. And so you instantiate one of these things or one of these gates as the software travels from, say, the vendor code. It goes to a development team. And the idea is that by placing these gateways in strategic places in an organization, you can quickly alert for potential problems, right? And so these gates should be easily interchangeable. And when something happens, really, you can communicate to headquarters and tell them, hey, something's going on here. So what is the objective of all of this work and what we're trying to do with, and hopefully that makes a little bit of sense at a very high level, the 20,000 foot level view of what these hierarchical quality gates are all about. What we're trying to do is really improve the quality of software systems as they move through the supply chain or their corresponding development or production environments. And this is something that spoke a little bit to DHS. And we wanted to, to leverage what solutions were already out there. And so we wanted to make something like this that was affordable, right? And so this is, and I can't overemphasize, the ability to leverage existing tools that you can plug into one of these operational models. So So what's PEAK? Okay, so PEAK is a platform for investigative software quality understanding and evaluation. And again, don't blame me for the name. This is one of my master students that decided to name this. And so what you see here, you know, it's basically going into a little bit more depth as you look at the picture on the right-hand side. You have a software product that we leverage that may be in an institution, an organization. That's what we deem the instruments. As the instruments measure things, the instruments could be in a continuous environment, continuous integration environment. A measure is produced. We capture that, and those propagate all the way up to product factors and quality aspects. Each of the arrows, as they travel up the tree, have weights. And there's different weights, there's different ways of creating weights for each of these different factors. And I'm going to tell you a little bit about a couple of them. But this is one area that we're also investigating with AI and machine learning techniques to see if we can improve on the weighting of some of these factors, because you can imagine that as the number of factors grows, the ability to come up with good weights, especially when you're using ratio scales, gets worse and worse as you do this particular work, right? So how do you create one of these trees, right? In order to create one of these trees, you have to go through a process as a developer, and this is something, of course, that we want to improve on. But the PEAK framework, really, what you see on the very left-hand side of the picture, when you think about any one of these models, is nothing more than a tree, okay? Very simple data structure. The PEAK framework is really, it's a library or a set of utilities. This is all open source. And so at the very top, you have the quality index. The very next level of a tree is really what we call quality characteristics. And so these are the very high level entities that you think about in an ISO model. And then the further you go down on the tree is where you start looking at the tools, right? So the middle picture is basically populated with weights. Of course, we're trying to work on using machine learning algorithms to populate these weights, but they can also be done manually by domain experts. And then at the very bottom, there's the process that you go through as a developer to instantiate one of these trees, right? And in order to instantiate a tree, you have to go through the process of hooking up the tools that you want to work in your environment, and creating the actual executable that you're going to place somewhere along your continuous development environment. Today, we're really working more in the, and I'm going to get into this a little bit, with microservices and things like that. This is where we want to deploy some of these models. The weights at the very high level of a tree, when you're looking at the root node and some of the sub children immediately below the root node, follow what is called an analytical hierarchical process, or AHP process. And basically, this is a matrix, a two-dimensional matrix, where we do pairwise comparisons of all the entities. And so, for example, if I wanted to look at a comparison between maintainability and security, and I deemed maintainability to be a lot more important than security because this is, not something that I'm worried about, maybe I give a 0.8 to maintainability. But then you do a pairwise comparison, say, between security and usability. And so you assign a weight, based on that. And so you can see that if the immediate layer below the root node has too many entities, the pairwise comparisons can get quite expensive. And going through a matrix when you're doing these pairwise comparisons can also be taxing on someone unless you're a domain expert in the software that you're trying to build a model for, right? And so these are some of the areas that we're trying to automate through machine learning. So let's look at an example of a PEAK model, an operational PEAK model. One of the models that we built, this is a master student of mine that has been working on this, is what we call the peak bin design. This is bin stands for binary. Okay, and what we're focusing on is on CWE 699. CWE is the Common Weakness Enumeration. I'm sure most of you, given the audience that I have here, are aware or know about CWEs. Organizes the CWE 699 organizes weaknesses around concepts that are really frequently used in software development environments. So this includes architecture and implementation. These views really, what they do is they simplify the navigation of CWEs from a particular perspective, right? The tools that we're using to feed into this peak bin at the bottom layer are CWE Checker. This is basically a suite of checks to detect common bug classes, things like dangerous functions, simple integer overflows, things like that. The main goal is really to aid analysts to quickly find vulnerable code paths. CVE binary tool scans for a number of common vulnerable open source components, things like OpenSSL, libpng, libxml. And actually, if you go to you can find the Wikipedia page for CVE binary. There's a ton of libraries that it scans. And then, of course, the error rules, which are a way of identifying malware, right, by creating rules that look for certain characteristics. And so what we decided to do is we're using those tools, and the model that we decided to use to inform the creation of our model, we use the Microsoft Stride model. And so the Stride model on the bottom left of your picture there, you can see that we're focusing on, think of the immediate node below the root node as being authentication, integrity, non-repudiation, confidentiality, availability, and authorization. Okay, so now we need to find, how do we populate the tree according to what we've created. So what you see here are the categories of the SWE 699. They basically become product factors in the tree. Product factors are really quality measures, product factors, etc. They're names that we give to the different layers of the trees, nothing to get too hung up on. And trees can, the rule of thumb is you want to make trees shallow. You don't want to make them too deep because the complexity grows significantly. And so you can see in here how some of these categories map onto a tree that we create. This is work that one of my students did. At the very high level, for example, here's what it looked like, the tree. All of these quality aspects right below the security quality index are going to inform a total quality index, right? And there's some of the definitions from Microsoft Stride. Again, you don't need to be an expert on Microsoft Stride to see what we're trying to do here. Okay. And that's another look at this as we get closer, as we zoom into some of the tools at the very bottom. Okay, so how do we know this tree actually works or is correct, right? So we need to have ways of validating, first of all, that the tree that you created somewhat captures what is happening. So if you have software that evolves over a period of time, and you look at version 1, version 2, version 3, right? You want to understand that when you see a vulnerability or when you see something happening, that the score that's reflected by some of these models is as a result of hopefully the worsening security of the system and not because of something else. And so we need to know if the score that's produced by the tools, right, is influenced by these factors and not other things that are not related to security issues. And so we ran a number of experiments. And one of the things that we did is we identified some of the metadata associated with a corpora of about 700 Linux binaries. We used this to create a benchmark. We created a repository, and after running multiple analyses, we ran a lot of experiments of this, we found that we have to take into account size, domain, and the linking strategy for a binary. And this tells us that a change in the score for a particular binary that you're testing, as it evolves through the system, right, over time, can see a higher or lower score due to these factors, and maybe not necessarily because of a security concern. And so we have to be careful with that. And so this is the reason we're looking at some of the metadata associated with binaries, to make sure that we need to account for that as we look at the security scores that are coming through. The other validation process that we're just in the early stages of looking at is when we synthetically introduce a disharmony or a malware or a bug into a binary, that is reflected correctly in the score that comes out on the security model. Okay, so we did an initial case study on something called BusyBox. Okay, we looked at 9 different versions of BusyBox, and we knew that BusyBox had been patched over a period of time, and we wanted to see if that was reflected on the quality scores or the security quality scores that we were getting. And so we were able to see that, and then we were able to identify where some of these things are coming from. And so at least this gave us confidence that the models that we're producing are actually capturing what is actually going on in the systems. Now, in order to visualize all of this, of course, we created a set of tools. Again, these are more the manager tools, right? So you're able to create also, this is just, eye candy, right? Basically, it's much easier to look at this than to actually look at outputs on a terminal. And so you can look at the TQI scores, you can look at each of the individual entities and see what the scores are. The colors that you see up there are based on the colors that CySER provides for different levels of security. And of course, you can look at the data in many different ways. We created a good scoreboard to allow people in the business side of things, meaning on the high layers of the tree, to be able to visualize the data and make adjustments accordingly. Again, what I usually tell people, don't compare scores between organizations. What you need to do is, the reason you have a lot of these types of tools are to look and learn about the trends of how your organization tends to score over a period of time. And so if you see a discrepancy on, a big spike or a big dip in some of your graphs from one day to the next, then it doesn't matter what the score is, but that should be cause for concern or cause for further investigation. And so really, this is in the context of your organization, and you get, as you work in an organization, you get a pulse for what is correct or what is the score for a particular entity that you're following. At the development level, this is hard to see, but you can look at the tree. I'm going to zoom into that tree, and you can look at the tree and debug every single node that represents, one of the suites, for example, in our case, that we are trying to track. You can expand each of these nodes. I have a video, but I'm not going to show it here, that one of my students put together. And that allows you to debug more at the developer level, right? At the tool level of the tree, to make sure that you can make adjustments or see if something is not being captured correctly. These were necessary tools for us, really, for us to be able to debug our own code. So what are some of the models that we're developing? So PeakBin is a model that we're developing in collaboration with Idaho National Labs and DHS. We have another model that's being developed for Army, which is a Peak C# model. C# seems to be a very popular language with many of the vendors with Army, and so they asked us to focus on that. We're also looking at a security version of the C#, which only focuses on security. And we're also, in upcoming work, we're going to look at microservices, specifically in the Azure world, for DHS, and to create some of these quality gates in that space. Here's just the view. I put this here just so that you guys can see them. The Peak C# model, this is what it looks like. Again, we took the entities out of the ISO 25K, And this goes one level deeper so that you can see some of the things that we're focusing on. Here's the PIC C# security. And this, again, uses some of the stride model and some of the, you're looking at the upper part of the tree. If I expand the full tree, you're going to see some of the different tools and disharmonies that we're focusing on. The tool that we're using here actually for C# is called Security Code Scan, and it's a tool that runs through a suite of tools called Roslinator that contains a whole bunch of tools that allow you to work in C#, and it's free. All right, so that's pretty much what we're doing with quality assurance. A quality assurance point of view, I'm pointing it at security and using our expertise in quality assurance to use it for, trying to understand the quality of a system when you look at it from just the security perspective. What is other work that we're doing in our lab? And I wanted to, I'm sure you guys are going to have some questions, but I'm going to leave that till the end. Some of the other work that we're doing in our lab right now, this is work that is being sponsored by Raytheon Technologies. Dr. Lemiers and I are working on developing quality models using this PEAK infrastructure to see if we can feed real-time binaries from PLCs into a quality model. This is a challenge, but we're trying to experiment with this. There are some tools that we're looking at to understand what looks like, what are good execution patterns or command patterns that look good. We're looking at tools, obviously we looked at Wireshark, but we're also looking at tools like Zeek and Suricata. And the second really interesting project that we have a couple of undergraduates working on, it's really, you look at this is what the picture is all about for AIM2. You have ladder logic at the very top of that picture. That ladder logic, when you look at that and you provide the processor architecture definition, we also create, we have a random number seed, and we feed this into HDL files, hardware description language files, and we created 3 separate processors with a voter. And so basically, since we know the processor architecture, we know how to scramble the opcodes for the processors, and the voter knows what randomization system we used. And so then we can synthesize this and put it in an actual FPGA on a system. So the idea is that if somebody was trying to subvert the system at the firmware level, they would also have to know the randomization process, because internally the voter would not agree if somebody couldn't figure out how we were randomizing this. And this is some of the nice opportunities that FPGAs afford us today. We did acquire, we don't have a facility here to do work in PLCs, but we are teaming up with Idaho State University, who has a significant facility to do PLC work, and of course with Idaho National Labs. We've acquired some simple PLC starter kits, and we actually found out that our processor, our FPGA processor here, is actually a very similar implementation to an Altera Cyclone FPGA. So we're hopefully going to make some progress in this space. Okay. The other work that another student, master student, is focusing on is on classification, clustering, and anomaly detection using graph representations. What you see here is it's the flow from an executable. We extract a control flow graph representation of an executable. Control flow graphs that look a little bit closer, right, are gonna cluster closer together. And what we do is we extract a representation of these control flow graphs using an embedding method called graph2vec. This is a software that you can actually find from a Python library, and it's freely available. And it's one of the ones that we've had the most success with. But the figure here basically illustrates the computational pipeline that we've used in order to first construct the graph representation of a binary code, and then to create a vector representation of the graph data, which can then be fed as input to a number of different traditional machine learning algorithms. The way we graph this is you can do dimensionality reduction so that you can see it in 2 dimensions. And there's a couple of algorithms that allow you to do that. When we did this, we looked at a lot of, we looked at a lot of different work that is currently going on in this area. And there's a lot of, we found a lot of powerful binary analysis tools that are out there to help us construct the control flow graph. We looked at Anger, BAP, Ghidra. There's a number of tools. We focused on Anger because it's a tool, it's a baseline tool that is used by software that INL also uses. And so we were able to create a lot of these graphs. Now, the term graph embedding is commonly used in graph analysis communities, really, and it generally refers to 2 different, but they're actually related approaches to representing a graph as a vector or as a set of vectors. We decided to use a single vector to represent an entire control flow graph, but you can use other software that's, for example, called node-to-vec that converts every node into a separate vector. We found much better success by using graph-to-vec, basically converting an entire graph into a single vector. We have run into issues where the control flow graph is too big, and so we ordered a new server to help us generate those. So some of the results, encouraging results, really, we've created we have a corpora of malware and benign software. The size of the malware binaries versus the size of benign software is something that's parameterized, and you need to tinker quite a bit, to adjust it correctly. But we used an algorithm called TSNE. This is an algorithm that's actually performed better than principal component analysis or PCA algorithms to help us reduce the dimension of the vectors so that we can visualize them. And we used 5. What we did is we created 5 very simple programs, like Fibonacci numbers, a sorting algorithm. And what we did is we created 50 variations of that algorithm. So a Fibonacci algorithm that we didn't change the functionality of the algorithm. So think of it as kind of like mutations, but the mutations are still good. And we created 50 different mutations of each algorithm. And that gave us a much larger corpus that we could use to see if we could use some clustering algorithms after you create the vector form to see if they would cluster together. And we were able to cluster all the graphs that, even though the graphs were different, graphs were close enough because the functionality of the code didn't change. And so we were really successful. Again, these are toy preliminary programs that gave us a really nice clustering technique. The idea is going to be to also use these methods to create a tool that can feed into some of the peak models for doing quality assurance, where each of the clusters, for example, could have a different severity that feeds into the particular model. So a summary of our preliminary results is really, we have really promising ability to separate this. We have promising results for standard anomaly detection. And we're using the graph-to-vec algorithm that looks at the entire graph, the entire control flow graph, for preserving similarities and different control flow graph that we extract from each of the binaries. Okay, so where are we going with all of this? I wanted to leave some time for questions here in a little bit. DHS was very clear with us that as we were starting to pitch a lot of this technology to them, they wanted us to focus on the cloud. With DevOps, basically, or SecDevOps, which is software development life cycles that incorporates operational people. As this becomes more and more prominent, we're creating software much faster, right? And so the turnaround on the software is a lot quicker. And so microservices have really started to flourish because you can create microservices very quickly. And so they're much easier to deploy, and you can interchange because they break down all these huge monolithic software applications, right? And so they want us to start focusing on seeing if we can put together some of these peak models that are more parsimonious, meaning they have to be very focused on one particular area of the quality of the different microservices. There are some tools that we found, not a lot. We're going to start by looking at Azure versus AWS. Azure is better in the software as a service space rather than the infrastructure as a service, where AWS is king. We're also going to focus on Docker because it's very popular. And so this is where we want to go. And there's, of course, 3 questions there that there are more than that, but these are some of the elements that we want to investigate in that particular space. There are 3 areas that we want to focus on within the, as we look at the cloud as kind of an underlying base for this work. And this is work in collaboration that we're going to work with Washington State, Rochester Institute of Technology, and Idaho State University. We want to specifically focus on measuring the quality and maturity of ICS and cloud-based software. For ICS, we're still waiting for DHS to let us know what exactly they want us to work on. But for cloud services, they want us to focus on Azure. For the second area that we're focusing on, one of the areas where there has been some controversy is that, when you buy a binary or when you buy some software, that, are you getting what you really paid for? And so one of the things that they want us to do is to look at a bill of materials, a BOM, and be able to take this apart and see if, does it really match what they told you that you were getting? And not only that, but we need to decompose this to see if the parts of, that make up the software, are they really, are they safe? Are there libraries that are known to have known vulnerabilities? And so we have to be careful with that. This is work that we are going to work with Washington State on. And we're going to use goal-oriented requirements, or GRL model dependency graphs. Here's some of the decomposition tools that we've been studying or looking at. We haven't really settled on any one of these tools to look at the different architectures as we do decomposition of some of the binaries. And then the last area that we're going to be looking at is the identification of security zones and sensitive sections of code. For this, we were asked to investigate SUI 200, which is a family of SUIs that provide exposure to sensitive information, right? And so this is an area that is pretty big, and we also want to use techniques that look at, this is also work we're doing with Washington State. We want to look at deep graph representations. Basically, this combines static and dynamic program information. Static information is kind of like CFGs or data flows, control flow graphs. If you've taken a testing class, you know what those are. And execution traces would be things like dynamic information, right? And so when you start to blend static and dynamic program information techniques, this is an area that hasn't really been explored too much. And hopefully this yields additional information when looking for identifying these sensitive sections of code. So this is another view of the decomposition of the SUI 200. We put this in a graph database just because graph databases are, I can't overemphasize this, it's a way to give you causal analysis, you know, of any 2 nodes, right? You can, if you have a starting node and an ending node, you can really follow a trace and see if there's a connection between them that allows you to look at all the hops in between that help you trace why something may be happening. And so they're extremely powerful, especially in cybersecurity. Okay, so here's some of our potential collaborators. In fact, we already know some of our collaborators in the work that's upcoming that we're doing. And the Applied Research Lab at Montana State, it's its own building. We put this together. This came on board about 1.5 years ago. We have the the space has 8 labs inside it. Each of them is about 1,000 square feet. These are your typical SCIF spaces with 12-inch concrete, and you have to get it accredited through through DoD, and it's a long process. They have to be self-sustaining. You have to have the ability to secure all the information when some of the work that we do tends to be classified. And so that's what, kind of what it looks like right now. And this allows us to also work with not just government, DHS or DoD or Air Force, but also a lot of the partners that we have that are coming in from industry, like Raytheon, Northrop Grumman, Lockheed Martin, and Boeing, which are the big groups that are working with us right now. So I'm not going to get into this. This is some of the expertise that MSU has over here. But that's pretty much the presentation. And so I'm going to stop here, and hopefully you guys have some questions. I'm going to stop sharing here. Or I can keep this open and come back to a slide if anybody has any questions on a particular slide. Thank you.
Thank you. So one question I had on the SCIF area, is that also available for possible collaborations if people came up and interacted with you all to be able to work with that if we don't have that established in our location?
Yep, absolutely. And this has been a big selling point for, it's actually opened the door just to have the facility to be able to say we can do this classified work. Without the facility, it was a non-starter in many conversations with DHS or DoD. We just had to have the facility. But absolutely no, it's open for collaboration.
Great. All right, I don't see any questions in the chat.
Can I go ahead? Yeah, I can go ahead and ask. Clem, very interesting talk. Thank you very much. I enjoyed many parts of it. I have a couple questions, but I want to ask the one that is more clearly close to what I do. So I don't do software engineering, but some of the things that you said at the end, the parts where you have many collaborators, brought many things to my attention. And so one of the last pictures you showed, where you had put things in the form of a graph database, has, graphs come up in some ways twice, right? And you've got this idea of having relationships that could be involving more than 2 partners. That's where the graph database would come in. And I don't know if you have thought about thinking of using hypergraphs. I don't know if you know what hypergraphs are. And there may be some things that are more convenient, and maybe if you work with things that have to do directly with your codes and you care about how efficiently things are done, there may be things we could chat on. So has hypergraph ever crossed your mind in what you're doing?
It has not.
Okay.
So this is great, and this is the reason why I like to collaborate, because again, as a software engineer, hypergraphs don't come up a lot.
Yeah.
But absolutely, I would love to talk to you more about it, Asifo. Yeah.
Yeah. So let's have that one, and the other one is a quick one. So I like the word pick, the one that your student came up with. It's a good name. So ideally, you are interested in having these scores, right, for these different things of interest, and they made sense to me. I don't know the details, but they made sense to me that you've got a way to look at them, and there are scores and so on that could be seen more as relative values, where your changes are more important than the actual ones, right? Yep. What I didn't get, and you probably have said it, is the metrics that you were working, where you come up with pairwise comparisons between 2 LTs.
Yeah.
What is the motivation for having to see a pair at a time? Why isn't the score on its own good enough? Why do you have to see 2 things at one time to do anything with them? What's the motivation there?
No, so this is when you're starting to build a tree, at the very top of the tree. Let me see if I can bring up a tree here. Let me put it up here. Okay, so at the very top of the tree, where on the right-hand side, you see, say, portability, maintainability, and security. Maybe these are 3 quality aspects that are part of the model that you want to use. But let's say that you have no interest in security because this is a toy piece of software that who cares who uses it. And so what you do as a manager, you're going to create a matrix that has all these three quality aspects in the columns and in the rows. And you're going to compare, obviously, maintainability against maintainability is just a one. It's a diagonal matrix. But when you compare maintainability with portability and all the other ones, you do these pairwise comparisons. What you're doing is saying, this is more important than the other one. And then the tree, the weights associated with each of these things get populated according to how you decided to do that. There may be cases, for example, where you couldn't care less about, I don't know, network issues or something. And so there may be a quality aspect that you really want to give a zero weight to. And so you would, everything else would be much more important than that one.
So what's the point in having two at a time is my question. Why isn't the score for something that you care about is there, and so regardless of the others, you've got that one. Right. What is it that forces you to see two things at a time?
I think that you can always compare two things and kind of weight more accurately which one is more important than the other. I think I've seen papers where they talk about anytime you start comparing more than even 5 things, like a Likert scale, it starts to lose fidelity. So you're never going to see a Likert scale with more than 0 to 5, right? 1 to 5. It's rare that you see a 10 because the difference between a 4 and a 5, is it the same as the difference between a 7 and an 8? You don't know. Your fidelity gets worse and worse the more things you have. So when you have pairwise, we know very well how the two compare to each other. Of course, that has the problem of pairwise, you have a combinatorial explosion there. And we are thinking of ways of making this easier by maybe creating a table of just the things that you care about. We're experimenting with this, but that's a great observation. Yeah.
All right. Thanks. Mm-hmm. I don't want to take up too much time. Thanks a lot.
Yeah, Noah had a question. Noah?
Yeah.
Oh, yes. I typed it briefly in the chat here. My question is, you mentioned a little bit later in the presentation about effectively plotting these binary executables, right? And giving their, putting them down on a vector space and then doing, running analysis on them. My question is if you're going to implement artificial intelligence with that, would it be possible, and there's just plenty of ways to do that, but suppose after you do with that, and I'm looking at Firefox exe and I'm looking at p1.exe, and if the x, if the x2, if that variable holds, it would look like that's pretty much a lot more like Firefox than it is, grep. And if it's a lot more like Firefox, then it would be, like something with a Firefox at the back door. But my question is, if you were going to run analysis on them, if you were going to implement machine learning, would it be possible to hook it up to a generative adversarial network to actually create these malware payloads?
Yes, you could. Now, I'll be honest with you, I haven't looked at adversarial networks, and that's a very hot topic now. There are a lot of areas that we haven't looked at. Absolutely, you can do a lot of these things. This is, this is really open right now for discussion, and this is one area where, where we've found that this control flow graph tend to capture additional semantic information that goes beyond just structural information. But to be honest, in terms of which specific machine learning approaches to use, the door is wide open, and I haven't done any more research than that. I'm sorry I can't answer your question anymore in any more detail, Noah.
Oh, that's fine. Thank you. Thank you.
Okay, there's one more question here from Haiping.
Hi, Haiping.
So it's how were the binary code security metrics computed given the binaries are often stripped and hard to extract information from?
Oh, I think, Haiping, can you speak?
So Clem,
yeah.
Glad to see you again. Yeah, so yeah, really very many interesting ideas. It's definitely one of the most interesting topics to me. and a lot of good ideas. So you mentioned in one of the slides before that you were looking at some scoring mechanisms for measuring the security of binaries. But as you know, many of the industrial binaries are shipped with a kind of stripped format, which means they are actually not the original format produced by the compilers. They're having a lot of things, a lot of fat removed. Yep. But that also create a lot of, because they are optimized, the format, a lot of information is gone. It's a little bit hard to do. So it's very hard to extract even some basic information from binaries. For example, it's even hard to extract the function names. You cannot even extract that, or even control flow graphs is not trivial to reconstruct either. So I was just wondering, how did you compute those scores for binaries?
Well, for this is because so there's a couple of things that we have access to the code that gets compiled first into the executable, right? And so we can look at that, and then that's how we're training some of these things, and we have access to that. But when you look at a binary that comes from a third-party company, and we've done this already with some of the PLCs, we come across exactly the issue that you're talking about, where we cannot even run some of these tools on them because it's not just packed, the binary, but it's also encrypted. And so we have a big problem in that particular space. I'd love to have an even longer conversation with you about this, because that's a really hard problem. If a binary is encrypted, there's not much we can do, unfortunately.
Yeah, maybe we can look into that later. Yeah. So yeah, I have some possible ideas to help with that area.
Yeah, and this is one of the areas that I look forward to working with you on, Haiping.
Yeah, thank you, Clem. Yeah, thank you.
Well, great. Well, we've run out of time, which is a good thing. And I heard a couple conversations where people are going to follow up. So that's even a better thing. But thanks, Clem, for an excellent presentation and a lot of good discussion. Thanks, everybody. This is our last webinar of the semester because of the just the end of the semester and exams and different academic schedules that we have across our different partners. But we will ramp back up in January. So we wish you all the best for holidays and look forward to a great 2022. Thank you.
Thank you, guys.
Thanks,
Thank you.
Thank you, Clem. Thank you, everyone. Thanks, Joel.